Hi guys, this is a second video on calculating Kc. This will explain how to do the questions where only some of the substances' equilibrium concentrations have been given. Remember to do a question to calculate Kc. The equilibrium concentrations of all substances, i.e. all reactants and products, must be given. So sometimes you might see a question including words such as allowed to approach equilibrium or when equilibrium has been established, and you're only given the equilibrium number of moles or concentration for one substance. If that's the case, what you need to do is use the ICE method or the table method. I stands for initial, C stands for change, and E stands for equilibrium. So for example, you've got a question, an equilibrium reaction, 2A plus B gives you C plus 2D. In this question, you might be told some initial number of moles of A or B that have been given, and when at equilibrium a certain number of moles have been established or used up or are present. What you need to do for this ICE method is to create a table. Note how I've written the reaction. I've spaced out all of the reactants and products, so there's room underneath each one. You set up a table like this. Initial number of moles, change in number of moles, that's delta N, equilibrium number of moles, and equilibrium concentration. How do I get the change in number of moles? You're going to have to use stoichiometry, i.e. the Molar Ratio. And I'll explain how to do that when we do put some actual numbers in. Okay, for example, let's say you're told 5 moles of A and 3 moles of B were added to an empty container of a certain size. That immediately tells you that there are no initial moles of either product, so you write them down as 0. Then you're told in the question 1.5 moles of D was present at equilibrium, so you put it in the equilibrium number of moles. Now what's the change? From 0 to 1.5, you write plus 1.5. Because C has a 1 out the front and D has a 2, that means half the number of moles of C will be produced, i.e. only 0.75 moles of C will be produced, so you wrote plus 0.75. If products are produced, reactants are being used up. So because you've got 2A and 2D, they're in the same ratio as each other, you write minus 1.5 for A, and therefore minus 0.75 for B, because there's only 1 out the front. Remember what you do to the reactants, the opposite must be done to the products. So if you're making products, if their numbers are going up, the reactant numbers are going down. A very common mistake is to people just put minus, 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 or plus, 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 plus. Another common mistake is to not take into account ratios, i.e. they would have 1.5 for everything. Then you do the calculation, so 5 minus 1.5 is 3.5. 3 minus 0.75 is 2.25, and 0 plus 0.75 is 0.75. Now you've got the equilibrium number of moles for everything, but you need the equilibrium concentration for everything in order to calculate Kc. So you need to read the question, check the volume of the container, divide all those moles by that volume, and you can use this now to calculate Kc, to put these numbers into the K expression. So for example, in this case, it would be the concentration of D squared times C divided by the concentration of A squared times B. And this one would have no units because all the M's would cancel out. All right, I want you to pause the video and write down this question. This is from the textbook. Note it says when equilibrium was achieved. That means it wasn't at equilibrium in the beginning, so we have to set up an ICE table for this question. So write out the equations separating the reactants and products, so you've got room. Set up the ICE table, and then enter the information from the question. So 0.35 moles of dinitrogen tetroxide in the beginning, it doesn't say how much nitrogen dioxide in the beginning, so you assume 0. You have been told at equilibrium you've got 0.12 moles of nitrogen dioxide, so you add that into that box. Therefore, the change for nitrogen dioxide has gone up by 0.12, so N2O4 will have gone down by half that amount, because there's a 1 out the front instead of a 2. Do that calculation. Check the volume in the question. In this case it's 2 litres. So divide all those number of moles by 2 to get the concentration. Write out the K expression. So NO2 squared divided by the concentration of N2O4. Put the numbers in and you get 0.025 molar. Note the unit for this one would be capital M and it would be 2 significant figures. I want you to pause the video and write down this question. The equation will come in a minute. So here's the equation and I've set up the ICE table for you. What I want you to do now is to add the information from the question directly into the table. And you should have this. So 0.7 moles of PCl3, 0.5 moles of chlorine in the beginning. And the question also said at equilibrium 0.3 moles of PCl3 remain, so that goes into that box. Because it was an empty container, you have no product, so you write 0. What's the change? From 0.7 down to 0.3, it was minus 0.4. Therefore, chlorine will go down by 0.4, and phosphorus pentachloride, or PCl5, will go up by 0.4. Do those calculations to get the number of moles at equilibrium, and this is what you get. Check the volume of the container. Conveniently it's 1 litre, so the concentrations are the same as the number of moles because you're dividing by 1. Those equilibrium concentrations can now go into the expression, so you write out the equilibrium constant expression, put the numbers in and calculate it, and it's 13.3. This time the unit is m to the negative 1, and there are 3 significant figures for all the numbers in the question, so it's 13.3. Here's another question I want you to pause and write out. I've also written out the equation and the table for you and put the numbers in from the question. So you're told the original number of moles of sulfur dioxide, oxygen and sulfur trioxide. Pay attention to the volume of the container. It says allowed to reach equilibrium, so this will be an ICE table one. At equilibrium, 0.14 moles of sulfur trioxide remained. What I want you to do is to calculate K. Once you've calculated it, please come back and check the answers. So don't forget, the first thing is to do the change. So to go from 0.15 down to 0.14, it's minus 0.01. Therefore, sulfur dioxide will go up by the same amount, and oxygen will go up by half of that, remembering the mole ratio. So do those calculations, and there's the equilibrium number of moles. It's a 2 litre container, so you're dividing all of those number of moles by 2 to get the following concentrations. Here's the expression for the K, or KC. Put the numbers in and you'll end up with 726. You're allowed 2 significant figures because of the 2.0 litres in the question, so you need to put this into scientific notation. So it'll be 7.26 by 10 to the 2, and the unit will be m to the negative 1. What I want you to do now is to open up the booklet that's got the pictures of all the rates stuff on the front, and you'll find a page called Equilibrium Using Stoichiometry, and questions looking like this one. Do questions 1 and 2, they're pretty straightforward. Then if you're struggling with question 3, I'm going to go over it now. So add in all the original moles from the question. This time you have a look carefully. the concentration of hydrogen is found to be 1.25 molar at equilibrium. It doesn't tell you a number of moles, it tells you a concentration. So the 1.25 goes into the equilibrium concentration box, not the number of moles. We do need the number of moles of everything because we need to look at the change in number of moles. So remember N equals CV. The volume in this case is 2. So you need to multiply that by 2. So the equilibrium number of moles of hydrogen would be 2.5. Therefore the change is plus 0.5. CO2 will go up by 0.5. The two products will go down by 0.5. They're all in a 1-to-1 to 1-to-1 ratio. Do those calculations. Now we've got to get back into the concentration again. So this time we divide by 2 because of the 2 litres to get those concentrations, and we enter them into the K expression. Because the concentration of water gas and carbon monoxide are conveniently the same, it's going to be 0.25 squared, and same for the two products because they are conveniently the same as each other. So 1.25 squared, and you'll get 0.04. Two significant figures, and this time there are no units. So this is the last question I'm going to do in this video. I want you to pause the video while you write this down. The reason I'm doing it is it's quite different because you've got here 28% of the knuckle had decomposed by equilibrium, and it says calculate the KC. There's the equation. I actually want you to have a go at it yourself, see what you can come up with. However, if you get really stuck, I'm about to go over the answer. This time I'm not going to do an ICE table, I'm just going to take you through the logic. You're told the initial number of moles of knuckle is 5. If 28% of it had decomposed when equilibrium was established, that means 72% of it was remaining. So 72% of 5 is 3.6 moles of knuckle at equilibrium. So the concentration of that is 1.2 because I've got a 3 litre container, so I'm dividing by 3. The change in number of moles of knuckle is minus 1.4. I need to go from 5 down to 3.6. Therefore, the nitrogen oxide has gone up by 1.4 because they're in the same ratio, and chlorine has gone up by half of that, or 0.7. Because these were originally 0, all I have to do is divide 1.4 and 0.7 by 3 to get their equilibrium concentrations. And these are the numbers that we're going to need to enter into the K expression. So there's the K expression, NO2 squared times chlorine divided by knuckle squared. Put these numbers in, and there's the answer. Two significant figures, and it's molar. Thank you for watching. I hope this has helped.